Welcome back to the Datarekha audio guide. I'm Diya.
And I'm Arjun. Here's something that sounds impossible until you've done it. You can run a serious large language model on a laptop. No GPU, no cloud, no internet. And it's genuinely useful. The trick is one file format and one tiny program.
Okay, but I've downloaded models before, and they're these sprawling folders full of files. You need Python and a whole framework to even open. How does that fit on a laptop, let alone run on a CPU?
That's the right starting point. Because those files, the safetensors you get from Hugging Face, are built for the wrong job. They're a training format. Full precision tensors, sharded across multiple files, paired with Python and a framework. Fantastic for fine-tuning a model. Heavy and awkward for simply running one on your own machine.
So the format that runs locally is solving a different problem than the format that trains.
Exactly. And that's the whole insight. The local format is called GGUF, and it's built for inference. For running, not training. It packs everything one file needs into a single file. The weights, the tokenizer, the metadata, even the chat template. So a small C++ program can just memory map that one file and run the model, with no Python anywhere.
One self-contained file. So GGUF is what's on disk, and that little C++ program is the thing that runs it?
Right, those are the two halves. GGUF is the file. The engine is called Llama. CPP, a dependency-free C and C++ runtime. It maps the file into memory, offloads as many of the model's layers to the GPU as happen to fit, and just runs the rest on the CPU. And that tool everyone uses, Llama. It's basically a friendly wrapper around exactly this.
Now here's where I always get lost. You go to download one of these and there's this soup of names, Q4, Q5_K_M. What is all that?
That soup is GGUF superpower, and it's called quantization. The idea? Store each weight in fewer bits. Full precision uses 16 bits per weight. The quantized tiers go all the way down to about 3. The names just encode how aggressive you went.
So decode it for me piece by piece?
The number Q4, Q5, Q8 is roughly the bits per weight. Lower means smaller and faster, but more quality lost. The _K means the modern smart method, K-quant, which is much cleverer than the old round to the nearest approach. And the letter SM or L is small, medium, or large, where medium keeps the important tensors at higher precision instead of squashing everything equally.
So the famous one, Q4_K_M. That's roughly 4 bits, the smart method, the medium variant. Why is that the one everybody recommends?
Because it hits the sweet spot. 4 bits instead of 16 means the file is about a quarter the size. And yet, because the medium variant protects the tensors that matter, it keeps almost all of the quality. So you get nearly the full model at a quarter of the footprint. At the extremes, Q8 is near lossless but big, and Q2_K is a last resort for when memory is truly desperate.
So the real question is always, will this actually fit in my machine? Is there a way to know before you download 8 gigabytes?
There's a simple back-of-envelope formula. The file size is roughly the number of parameters times the bits per weight divided by 8, plus a little extra for the conversation context. So a 7 billion model at 4 bits is somewhere around 3.5 kbx. And there's a tool in the lesson where you drag your model size and your memory budget, and it sizes every tier and recommends the best one that fits.
And 2 things fall out of that formula, right? Quantizing never changes the parameter count. It's the same model, just stored coarser, and dropping one tier is usually the move that squeezes a model onto a smaller machine.
You just nailed both. The parameter count is fixed. A 7 billion model is 7 billion params at every tier. Only the bits per weight change. And dropping a single tier is almost always what gets you over the line onto a tighter box. At a quality cost you get to decide is acceptable. That's the whole control surface.
So when is this the right tool? Because there's also VLLM and hosted APIs. When do I reach for local GGUF specifically?
Think of 3 different jobs. not 3 competitors. A hosted API is simplest when you can send data out and pay per token. VLLM is for serving many users at once on your own GPUs at high throughput. That's where page detention and continuous batching shine, under heavy load. GGUF and llama.cpp are for the opposite. Single user, local, often offline, a desktop app, an on-prem box with no GPU, privacy-sensitive data, or just tinkering on a laptop.
So the dividing line is really one stream on modest hardware versus a fleet of requests at scale.
That's the cleanest way to hold it. GGUF is optimized for one stream on a modest machine. It's not trying to be a high-throughput server. And that's a feature, not a shortcoming. Right tool, right job.
So the one sentence to take away?
GGUF plus llama.cpp turns a frontier-style model into one self-contained file you can run offline on a laptop. And quantization tiers like Q4_K_M are the dial that trades a few bits of precision for a model that actually fits your machine.
One file, one engine, the right quant. That's the Datarekha audio guide. Catch you in the next one.